Hello, stat students. Today we're going to look at how we can get the expected value and standard deviation, or also known as the mean and standard deviation, of the binomial distribution. So let's review a couple of things. First, a Bernoulli trial is a random event that has two properties. One is there's just two outcomes. There's only two things that can happen. It's either success or failure. That's how they're traditionally labeled. And very important, the probability of success never changes. We consider it to be constant. We write probability of success as P, little p, and so probably a failure, of course, would be 1 minus P. Sometimes you'll see 1 minus P written Q in some texts, but I'm going to just write 1 minus P rather than writing Q. And then let's a couple of lessons ago, let's remember the binomial probability distribution computes the probability of k successes out of n trials of a Bernoulli trial. So we're going to do multiple trials, and we're going to ask the question, what's the chance that we get 2 successes? What's the chance that we get 3 successes? And we had a formula for that. That was this messy thing. And remember that n choose k was this factorial. We have calculator shortcuts for these things. I just wanted to remind you these things. Let's continue. So first, I want to look at what's the mean and the standard deviation of just a single Bernoulli trial, if we just do one trial. So, and for purposes of my example, I'm going to assume the probability of success is 1/3. So maybe you're playing a game and you're rolling a die and the chance of getting a hit is a 5 or a 6. I've played games like that. So that means you'd get a hit on a 5 or a 6, you'd miss on a 1 through 4. So your chance of success is 1/3. And because I have nothing better to do with my time, I just said, well, let's simulate this. So I used random.org and simulated this Bernoulli trial over and over and over again. And here are the results. I had some good time writing all these out. So here, black zeros represent a failure, and red ones represent a success. So there's my fairly robust simulation of this Bernoulli trial. 1 is a success, 0 represents a failure. So there's 2 questions I want to ask about this mess of numbers. One is what's the mean number of successes per trial? And of course I don't mean what's the mean number of successes of this particular list here. I mean, in the long run, if we were to do this many, many, many times, what is the mean number of successes I would get per trial? And that's actually, hopefully, obviously straightforward. Since my probability of success is 1/3, my mean is 1/3. On average, I'll have a 1/3 of a success per trial. 1/3 of these will be 1s, 2/3 will be 0s, and so on average, I'll have 1/3 of a success per trial. A trickier question is, with what standard deviation? And first I want to make it clear what this is asking. I'm asking, let's say I had this long list of 0s and 1s. It went on and on and on and on. 1 represents a success, 0 represents a failure. And I say, okay, what's the standard deviation of this massive list of 0s and 1s? We're going to compute the variance from first principles here. Remember, the variance, what we're going to do is we're going to say, okay, 2/3 of the time we're going to get a 0 on this list. So there's my 2/3. 2/3 of the time I'm going to get a 0. And then to compute the variance, we say, well, 2/3 of the times we get a 0. And then we say the squared distance from the mean. Remember, the mean we computed up here was 1/3. So we say 0 minus 1/3 squared is the squared distance of the mean from 0. And 2/3 of the time, we will have that squared distance from the mean. So 0 minus 1/3 is how far 0 is from the mean. We square that because we're computing a variance. And I say 2/3 of the time I'll have that number on this list. And then, of course, 1/3 of the time I'll have a 1. So 1/3 of the time, my distance from the mean squared is 1 minus 1/3 squared. And that's it. That's my variance calculation. It's the weighted average for the squared distance from the mean. And if I do some arithmetic, that's 2/9. So of course that's the variance. Standard deviation then is the square root of 2/9. We're not going to assign a lot of meaning to this number right now, but we're going to put this to work in the next slide or two. So, now what I want to do is I want to generalize. What if I replace p equals 1/3 with just p? What's my probability of success is p? Maybe it's a half, maybe it's 0.78, maybe it's 36%, whatever. I want a general formula. So what would change in our work? Well, let's look at our. We're going to let P represent our probability of success. Let's look at our work from before. This is the work we wrote down before. And I want to say, what changes if I replace 1/3 with just P? Well, first, here, instead of 1/3, I'll have P. So the mean will be P. So that's my first change. The answer to the mean question is the mean number of successes per trial is now P instead of 1/3. That's pretty straightforward. Okay. The second is what happens to the very standard deviation calculation. Okay? So, let's look at this part first. What would change here? Well, this 1/3 was probably a success. It was the fraction of the time we got 1s, and we're going to replace that with P. And then here, this is the squared distance from the mean. But the mean is also no longer 1/3. The mean is also P. So I have to replace this with 1 minus P. So the mean turns into 1/3 turns into the mean P. So this term turns into P times 1 minus P squared. We have a similar thing happen over here. 2/3 becomes 1 minus P, and 0 minus 1/3 becomes 0 minus P. So here is my variance. And I want to simplify that. I don't want to leave it like that mess. So the first obvious step is that 0 minus P squared is just P squared. And now we could square this out and distribute out all these parentheses and collect terms, but we're going to be clever. If you'll notice, there's two terms here. Both terms have a factor of P, and both terms have a factor of 1 minus P. So I'm going to factor those out. I'm going to factor out the P and the 1 minus P. From the first term, if I take those out, I'm just left with P to the first power. Second term, when I take those out, I'm just left with 1 minus P to the first power. And of course, if I look at that stuff in the brackets, I go, oh, that's 1. And so I get P times 1 minus P is my variance. And therefore, the standard deviation is square root P times 1 minus P. So that is the variance and the mean. Variance and the mean for a single Bernoulli trial. Average number of successes per trial is P. That's the standard deviation. So there's my summary. Now we want to go on, though, and ask, well, what if I do n trials rather than just one? That's what the binomial distribution is about, is, okay, I do 70 trials. What's my probability of getting 36 successes? I want to know what's the expected value, what's the mean. What changes? Well, I want to put my whole simulation out of here. I don't want to write it all out again. Let's do this fast. Boom, there we go. There's my simulation again. And we're going to let n here, for purposes of my example here, be 5. So what I'm going to do is I'm going to take this, I'm going to divide it into clumps of 5, etc., down the line like that. So this is like a binomial with n equals 5, and probability of success is 1/3. And if I look at the first clump, I have 3 successes. So I got 3 successes out of 5. If I look at the next clump, I got 1 success. So I got 1 success out of 5. The next clump, I got none. Those are all zeros. And so on and so on. So if I write all those down, how many successes did I get out of 5 trials? I get that list. And what I've created here now is I've created a simulation of the binomial distribution with n equals 5 and p equals 1/3. So my question is, what's the mean and what's the expected value of that? Before I look into that, though, I want you to note something. If I plot these frequencies here, my simulated frequencies on this list here, I get this plot. I had about, what's that look like? Looks like about 16%, 18% zeros, so on and so forth. This is the simulated binomial distribution. If I compare that to the theoretical binomial distribution coming from the formula that we had on the first slide that computes binomial probabilities, we see that it's a pretty good match, even though this trial's only got 50 values on it. We've got a few more zeros than we would expect, and a few less ones or twos than we would expect, but it's pretty good for we compare the theoretical to the simulated probabilities. Anyhow, let's move on. So what's the expected number of successes here out of 5 trials? That hopefully is intuitive. Since the probability of success is 1/3, for 5 trials we expect 5 times 1/3 successes per 5 trials. That's 1 2/3 success. On average, since we've got 5 trials here, and there's a 1 in 3 chance of success, we expect a 5/3 chance of success. 1 2/3 chance of success. That's just 5 times 1/3. Now let's get rid of the 5 and the 1/3. What would this be if I replace this with just P and N? So that would become probability of success P. This would become N. That would be NP. So we get N times P successes per N trials. So there's our first formula. The mean for the binomial distribution is N times P. I'm going to summarize these later on. But what about the standard deviation? Well, I could think about doing it the way we did before, where I wrote out this mess where there was only 2 outcomes. We were doing one trial, it was either yes or no, 0 or 1. But that would be horrible in this case. I mean, look at this. For n equals 5, we could have 0 successes, 1 success, 2 success, 3 success, 4 success, 5 success. We'd have 5 terms here, and each would have its own probability. This would be a big mess. It's not a very pleasant way to go to try to calculate the standard deviation. So, we're not going to do it that way. We're going to be clever. Well, let's X represent the number of successes on just one trial. This is kind of a silly random variable. It's the number of successes if I do it just once. So X can only have 2 values, 0 or 1. I either get a success and it's 1, or if I fail to get a success and I get a 0. But from the previous slide, we know the standard deviation of that. That was the calculation we did in the last slide. The standard deviation of this single Bernoulli trial is square root P times 1 minus P. And then we make the clever observation that the binomial distribution with n trials is just n copies of this added up. It's see if there's a success, see if there's a success, see if there's a success, so we do that n times. So we get n copies of the binomial of this Bernoulli trial added together. And these are independent random variables. They have to be independent because the probability of success never changes. That's one of our assumptions about a Bernoulli trial. So that means I can use my theorem about independent random variables. Since all these trials are independent, the variance of this big sum is the variance of the first plus the variance of the second plus the variance of the third, all added together, and we have just n copies of the variance. But we can see the variance from here. We just square this so the square root goes away. So we end up with n copies of P times 1 minus P. So that is the variance of the binomial distribution. And therefore, the standard deviation of the binomial distribution is square root np times 1 minus p. Clever. So let me summarize. The binomial distribution with parameters n and p, this is simply saying n is the number of trials, p is the probability of success, has mean n times p and standard deviation square root np times 1 minus p. You should know both of these formulas by heart. You should memorize these, the mean and standard deviation of the binomial distribution. So let's look at an example problem where you could actually answer a question using these things. So here's the sample problem. I'm going to pause this and I want you to See if you can answer these. All right. Mean and standard deviation. Well, the mean, according to this formula, is n times p, right there. Number of trials is 450 trials, and we have a chance of success of only 3%, 0.03. So mean is 450 times 0.03, so on average we would have 13.5 successes per 450 trials. We don't always have 13.5 successes, though, of course. In fact, we can never have exactly 13.5 successes. Sometimes there's more, sometimes there's less. So there's a standard deviation that measures the spread from this 13.5 we have from day to day. And we have a formula for that. There's my standard deviation formula. And I plug in n is 450, p is 0.03, 1 minus p is 0.97. Calculator tells me the standard deviation is about 3.62. This allows me to answer this question. Is 25 wins on a day a remarkably large number? Well, we can see it's above average. The average is 13.5. But is 25 just a little bit above average, or is 25 a lot above average? And one way to answer this, we're going to learn about another way to answer it in the next lesson, is to use a z-score. We can say, well, here's the standard deviation. How many standard deviations is 25 above this average of 13.5? And so we can calculate the z-score for 25. There's my z-score formula. 25 successes minus the mean divided by the standard deviation gives me a z-score of 3.18. So that tells me that 25 is over 3 standard deviations above the mean, which is pretty remarkable. That would be unusual in most circumstances. So there's one example. Thank you for listening, and I hope you learned something.